Alright. God damn it. I'm always fine until I start talking. Alright, so here I'm going to look at the derivation of classical sets used in axiomatic set theory, like Zermelo-Fraenkel set theory, via this commutable batch process notation. Okay. So the naturals sets, I don't have a notation for sets. So what we're going to do, we're just going to like group them together with commas. Alright, so 0, comma, this. Right, so we're establishing our reference frame as 0, and then we're serially adding the unit vector in that dimension k times, but k is a separately measured value, so it's not necessarily a value that you can find with respect to 1. So what we're going to do is we're going to chop off the fractional part of k at the end of this process. So we'll get, instead of getting k back, we're getting the lower bound, we're getting the integer part of k. That's what's happening. Okay. So this yields 0 and the unsigned unit numbers. Alright. The operation frac n returns the fractional part of n. This is a holdover from legacy notation that still needs to be redefined in the current notation. And I just set this up really quickly, so there's probably mistakes, but I really didn't even want to try to think about how to define that just yet, so I'm just going with with that for right now. Integers. Well, we have 0 and that. Oh yeah, so here we're taking the absolute value of it because it's unsigned. So here it's the same thing, we're just not taking the absolute value of it. So it's signed, so we get, this yields 0 and the one-dimensional unit vectors. Now this is actually pretty standard, but I just wanted to note it. Plus minus indicates a choice between signs per selection. Minus plus indicates the inverse choice is made on the subsequent item. So here, whichever sign we put on frac k is the inverse of the sign that's occurring here. So that we're always coming back to a whole number instead of like just doubling the fractional part accidentally. Right? We don't want to do that. Okay, so the rationals are 0 and all of this noise. So here we've got, basically this is doubled for two variables. We're dealing with a multiplication or application, right? So this is our magnitude part, this is our unit part, indicated by this symbol and this symbol. But internally, both they're pretty much the same, right? So these are sums. These are, what these are is the integer definition here, excluding 0, which is really easy to do because I artificially included 0 in the first place. So to exclude 0, I just don't artificially include it later on. Oh my god, look at that. So the way I'm defining the rationals is now not a contradiction. Right? Fucking Christ. It's not integer divided by integer. It's unit vector divided by unit vector. One-dimensional unit vector divided by one-dimensional unit vector. The results of that and 0. Right? So 0 is added separately to all of this. And here we just have a variable change because whatever we set k to, we want the denominator to be a different one, or to be able to be a different one, so different variable name there. Alright, so this yields 0 in the ratios between the one-dimensional unit vectors. Note that k cannot be 0, and thus the divisions defining the rationals here contain no paradoxes. This is because 0 has no magnitude, so if k is 0, then k doesn't exist by definition. Okay, so part of what's happening here is we're understanding what the fuck 0 actually is. right? That is an integral part of how we're defining this correctly now. Now the reals, okay, this one is fun. So we're including 0, and we're also taking basically this part here, right? So this, what naively looks like the successor function, but it isn't at all the successor function. Because k can be anything, literally anything, we have to filter off the infinitesimal components. So we're just going to, so this notation here is indicating that we're employing both addition and the positive and negative vector form of this simultaneously, right? So we're adding and subtracting simultaneously per iteration, per time we're operating through this. Here we're choosing positive or negative. Here we're doing both. Okay. So, and here we're using a function. X times the infinitesimal unit is y. So what it's doing is it's stripping off all possible infinitesimals from the resultant value here. And then we're reassigning that back to k. We're taking the result of all of those stripped values. Every single possible one of those is then reassigned back to k. So you end up with an infinite number of values of k. And this is what renders the reals continuous, despite being Archimedean. Okay? So this yields 0 and the one-dimensional measurable vectors to a tolerance which excludes the infinitesimals by way of reassigning a modified value of k, stripped of any infinitesimal part, back into k, so as to artificially render the reals continuous, despite lacking any infinitesimal component. Okay? So look at all of this extra work that we have to do. We have to do a lot of weird things to get these classical sets. For one, we specifically have to add 0 every time. Now, let's look at a reasonable derivation of classes. Oh, look, here's the numbers. It's basically the same thing we have here for the naturals, except we're not artificially including 0, because 0 isn't a number. So this yields the unsigned numbers. 1, 2, 3, 4, 5, 6, 7. Oh my god. Magnitudes. Here we're just not subtracting off the fractional part. So we're still stripping it of its sign. We don't need that. It doesn't need to be like that. Okay, so this yields all the unsigned magnitudes. Okay, so this would be what we normally use pi for. We usually don't deal with pi as positive or negative. We just deal with it as a magnitude. All right, that's what this is for. Okay, unit vectors. So notice that this looks a lot like the integer thing, or we just didn't artificially include 0. Okay, and it's very much this, except we now get sign at the end of it, so it matters how we're handling the signs. That's really the only nuance that has to be added to this. Okay. Now the infinitesimals are also a class, so what this will do, this will give us specifically the infinitesimal space around every possible value of k. That's what this does. So this yields all one-dimensional infinitesimal vectors. And we can get the measurables. So this is a lot like what we did for the reals up here, except we're not reassigning after stripping off the infinitesimals, and we're not including 0, because 0 isn't a vector, and we're not having to hide the fact that we fucked everything up by reassigning an infinite number of values back to the original value that we claimed we're dealing with all along. right? So we don't have to lie about things. We don't have to lie and say that 0 is a vector, right? This term, 0 vector, this is like common in like abstract algebra and physics and shit. I'm like, what the hell are you talking about? 0 isn't a vector. Shut the fuck up. Okay, so this yields all one-dimensional measurable vectors. So this name kind of goes back to my comment about like how the reals they're not that poorly named, right? They're like the realizable numbers, extended beyond realizability, actually. But so the way that they are realizable is that they're measurable, so we'll just call them the measurables, right? So now we get different names for everything. Okay. This is roughly analogous to the reals, except that it doesn't use variable reassignment to artificially appear to be continuous despite being Archimedean. Alright, now, the one vectors. This definition is the simplest. It's basically the same as the magnitudes, except we're not taking the norm of it. Okay. So, and this is actually why there was the plus or minus here, because it doesn't matter. And it wasn't wrong to have it this way. But the reason that I had it that way in the first place is because just to make it mirror this perfectly, because the only thing that changed now is we're not taking the norm of this, we're keeping it as a vector, right? So this yields all one-dimensional vectors. And look how simple that is. Look at how simple that is. We don't have to tinker with it. We don't have to fuck with it. It's just there. And note that absolutely none of these include 0, because these are classes of vectors and vector magnitudes, and by definition, 0 is neither. This results in later being able to derive rules from these classes without having to constantly waste energy making up ad hoc rules to treat 0 differently. It's almost as if I know what the hell I'm doing. Look at that.